minutes into the class, and then someone said, "Are you recording?" I said, "Oops." Okay. Well, actually, I should have called roll first. It's going to take a while to mark. Well, if I get on the right page, it'll take a while to mark.
Take even longer on the wrong page.
What's that?
It'll take even longer on the wrong page.
Yes, exactly, because I couldn't find you. Catherine and Clark, 2 C's. All right, and today's the 18th. All right, and this is one of those good, I don't know of many announcements. I guess this may be one if you're interested in it. On the Birmingham West Campus, technically, but it's right across the street from the East Campus, they've opened a new building called the Student Success Center. So if you're ever over there, I haven't been inside, but from the outside, it's huge and it's impressive looking. And from what I can tell, there's only maybe 1 or 2 classrooms in it. It's all student services stuff, you know. But I think we might be able to squeeze 1 or 2 classes in there. We'll see. Okay. The only other announcement I know about is one of these good news, bad news situations. The good news is next week is spring break week. And the bad news is that means we won't be meeting any next week. So get over it. Okay. So we'll go from there. All right. We just have one more example to do in 11.4. Chapter 11 is vectors and geometry of space. 11.4 is the cross product of 2 vectors in space. And this was, the volume by a triple scalar product. And right before we ran out of time last time, I tried to cram down my salad. I got about half of it eaten in the few minutes I had between after the guy left. And so I ate too fast and it's getting to me now, sorry. The geometric property of the triple scalar product, okay? The volume V of a parallelepiped, which means it's sort of like a 3-dimensional parallelogram. A parallelogram is a figure, a plane figure, 2 sides are parallel, the other 2 sides are parallel. That means the 2 opposite sides are the same length, same direction, 2 opposite sides, same length, same direction, with not necessarily equal angles, okay? In other words, not right angles. Well, the same thing is true of a parallelepiped. You have a face here and a face here that are parallel with each other, same dimensions. Face here and face here that are parallel with each other, same dimensions. And a face here and face here parallel with each other, same dimensions. Okay, that's a parallelepiped. With vectors u, v, and w as the adjacent edges. So, which I had something that could look like this, but I don't quite. I might be able to squeeze something if I were to hold this like that, and you could imagine this is closed here, here, and here. It's not very much of a parallel, but it is a parallelepiped. It's not angled 90 degrees here anymore, okay? Then pick any point, that point right there, x, y, z, or z, okay, up here, or u, v, w. Okay, it's not x, y, z because they're not perpendicular, but u, v, w. The volume of, with vectors u, v, and w as adjacent edges, one going in one direction, one going in each of the other 2 directions, okay? Then the volume would be the magnitude, in case you got one of these backwards, of u dot v cross w. Remember, the cross has to be in here because that's a vector, and you can dot a vector with a vector, okay? You'll get a scalar, which a volume is a scalar quantity. You may wind up with a negative if you do this one as a left-handed rather than a right-handed system. Then you're going to get a negative here, you know, but that's okay. Take the absolute value off. You can't put the dot product inside the parentheses because that would be a scalar. You can't cross a scalar with a vector. So you have to cross inside the parentheses and dot outside the parentheses. And then take the absolute value. So with that in mind, find the volume of the parallelepiped shown in this figure, which is U is the side of this edge over here, and that's going from the origin, okay? You don't have to be going from the origin, but this one is. U is 3i minus 5j plus k. V is the one going down that way. No I component, just 2j minus 2k. So you're in the xz plane, yz plane over here, not anything on the x direction. And then the w is 3i plus j plus k. Okay, 3 in the I direction, the x direction, and then 1 up and 1 over. Okay. So, with those three as the adjacent edges. Does it matter which one of these you put as the dotted and which one or two are crossed? No, it doesn't. The absolute values are going to take care of if you've got them any out of order. Now, according to the formula, it's U dot V cross W, which is just fine to do, but you can do any one of the three. So, which way you want to do it? The way the formula said? Okay. V is equal to absolute value of the U vector dotted with the cross product of V and W. Okay. Absolute value of those. All right. Let's do V cross W first. Now, to me, the easy way to do V cross W is I, J, K, I, J. Repeat those first two. The book doesn't do it this way. To me, this is the easy way to do it. Then do the V. There is no I, so it's 0I, 2J, minus 2K, 0, 2. Just repeat the first two. And W is 3, 1, 1, 3, 1. Repeat the first two columns. Okay? And we'll do sort of like a determinant. You don't have to put the bars in there, but I will. Okay? And you multiply the down diagonals, the positive of that. What would that be? What's that?
Actually missed our last class.
All right. This is 2 times 1 times I. 2I. Okay? See it? Okay? Then do a down diagonal here, and that would be a minus 6J. See that? And then do the last down diagonal there, 0K. Okay? No K there. Then do the 3 up diagonals, but these you're going to subtract. So that's going to be a minus 6K, because you're subtracting. It would have been a minus 2I, but you're subtracting, so it's going to be a plus 2I, and then nothing on J, because of zeros in there. So what do you have? 4I minus 6J minus 6K. Okay? Now, frankly, I find component notation far easier to do dot products, so I'm going to go to component notation here. Put it in angle brackets, 3 minus 5, 1. Dot that with what I just got, 4 minus 6 minus 6. Now, actually, I'm real tempted to just pull out a 2 out of that, and then, but I'll withhold. Resist the temptation for now. Let's just add these together. That'll be a 12, right? Plus 30 minus 6. Okay? 12 plus 30 is 42 minus 6 is 36. Yep. That should be the volume in whatever units these things were measured in of that parallelepiped. And that's what they got to. Good for them. Okay. Now, they throw a little thing in here. Oh, let's see how they do it. And then I may not have to say that if they're going to say it. Okay. Let's see how they did it. They use the same notation as before. We could have done any one of the three with any one, we could have mixed those up as long as you get each one of them in somewhere there. Okay, and there is the determinant there that they list, or the absolute value. No, that is a determinant notation. And here's how they do it, and it's perfectly good. Okay, you just have to keep this in mind. It would be 3 times the determinant of this down here. It's 2 negative 2, 1, 1. Okay, so that's going to be the first thing they do. 3, 2 negative 2, 1, 1. Now here's where you have to remember, and frankly, I would not do it this way. Even if I were doing this method, I would not go across like this, so it's perfectly legal. You can use any row or any column. I would choose this column. Why? Because it has a 0 in it. Okay? I'd do 3 times that, minus 0 times its thing. That's going to be 0, and plus 3 times this one. Okay? Let's do it that way. Okay? This will be fairly easy this way. This one times, wipe out the row and column, times the determinant of 2 negative 2, 1, 1. Okay? Lose the that line. And then I'm going to go through it in a little more detail. Then I do a minus 0 times this one. But 0 times anything is 0. And then it's plus 3 times what's left over there. Minus 5, I can't write. 1, 2, minus 2. Okay, let me see if I can make that look a little bit better. Okay, just a tad. Okay, now let's do the determinants. That's 3 times, this is 2, minus 2 is, no, minus a minus 2 is 4, plus 3 times 10, minus 2 is 7, okay, and that would be 12 plus, whoa, oh yeah, 21. No, it's not coming out right. 2 plus 2 is 4. 10 minus 2 is 8. Duh. All right, and that comes out 36. See why I like to do it the other way? No, okay. It comes out the same way. They are going to go across this way. And doing that way, you have to remember it's plus, minus, plus, minus, minus, plus, minus, plus, minus, plus. Any way you do it, always do it. As long as you go right or left, up or down, don't do diagonal with that. It won't work. They go across this way, so it's plus, minus, plus. And that's what they're going to show here. Plus, minus a minus 5, and then you do what's left over and you wipe out if you're going across, and you're using this one, you wipe out that row and write that column. And that's, they do a minus 5, and then the determinant of what's left here. 0 minus 2, 3, 1. 0 minus 2, 3, 1. And then finally on the last one, it's a 1 times wipe out that row and column, and it's 0, 2, 3, 1. 0, 2, 3, 1. And it's a plus 1 then, because remember, it's plus, minus, plus. Okay. The way we did it was plus minus plus. With minus 0, there's nothing, so you just have 2 pluses. You get the same answer however you do it, okay, if you do it right. Okay, that's the caveat there.
Can you explain the way you did it real quick?
Okay, this is the other way to do a 3 by 3. It only works for a 3 by 3. Okay, now, okay. Now, okay. All right. The triple scalar product, okay, let's go back. This one. Here's your triple scalar product, which is u dot v cross w, okay? So you put your 3 components of u up here, v here, and w there, okay? That's what we were doing. I didn't go back to show this, but that's what we're doing. And that's, these vertical bars mean a determinant of that. The determinant is, and this is, you're doing a, and I should have done mine this way too. I didn't even think about it. When you're doing, because I broke it down and did this one and then dotted it, okay, which is fine, okay, but it gives you the same answer if you do this. So I'm going to do mine the other way. We're just saying how to do it. Pick any row, any column, and if you pick this row, then wipe it out to begin with, and then when you do the 3 columns, wipe them out individually. Or if you do this column, then you wipe that out, and then wipe these rows when you do them individually. You know, that's how you do it, a 3 by 3. Now I'll show you the other way to do it, how I should have done mine, okay?
I was actually talking about the
Yeah.
diagonal.
Yeah, right. That's what I'm getting at now. Okay, whoops. Oh, wait. Have I gone the wrong direction? I think so. Triple scale, yeah, I was going the wrong direction. All right, let's do mine the way I should have done it, okay? You do the determinant of u, v, w, just like these. 3 minus 5, 1, right? But repeat the first 2 columns. 3 minus 5, okay? Then do the v. 0, 2, minus 2. Repeat the first 2. 0, 2. And then the w is 3, 1, 1. Repeat the first 2. 3, 1. Okay? Now, I'm writing it as if that's a determinant, and that's what we're doing, but we just elongated it, and this removes the necessity for you to keep up with the plus and minus, plus, minus, plus, minus, plus. It wipes that out because you just take care of it. Here's what we do. Do the down diagonal, multiply those together. That's 6, right? 3 times 2 times 1, right? Then do the next down diagonal. Minus 5 times minus 2 is positive 10, plus 3 times 3 is 30, plus 30. Okay? Then do the last down diagonal. That's a 0 because of that 0 in the middle one, right? Okay? So we're finished with those. Now let's do our up diagonals. Do you want me to erase those construction lines there so they don't? Okay. The up diagonal would be another 6. Only it's a minus 6 because the up diagonals are always negative. Okay, so that's a minus 6. The next up diagonal is a plus 6 because it's a minus 6 here, but you subtract it, so that's a positive 6. And then your final one is a 0. Okay? Because that has a 0 in it. Now add those together. Well, plus 6 minus 6 adds a 0, right? So that gives you 36. To me, that's easier than doing the individuals. Okay. And that's how you do any 3 by 3. If you're anything beyond that, won't work. Okay? Anything smaller than that won't work. 3 by 3 only. This is one way to do it. The book didn't show you that, but I did, because it's just the easiest, to me, the easiest way to do a 3 by 3 determinant.
A 3 by 3 means the
3 rows, 3 columns. Huh?
UVW.
Yeah, they're all three-dimensional vectors. Okay. If you had, but for a triple scalar product, it has to be three-dimensional vectors, because you can't have a three-dimensional structure like a parallelepiped in 2 dimensions. Okay, so it has to be 3 dimensions. And since that's where we live most of the time, you run into this a lot. Okay. Now, did we finish everything they did? Oh, we didn't do it their way, did we? Okay, let's do it their way now. 3 times, and you see where they got them. Whoops, wrong way. Let me erase mine so you... Okay. It's this one times the determinant that's left over down here, minus a minus 5 times the determinant that's left over here, plus 1, because plus minus plus, times the determinant that's left here, and that's what they get top of that page. And then let's do this. And remember, your determinant is positive on the down diagonal, negative on the up diagonal. That's 2 minus a minus 2, which is 2 plus 2 is 4. High level math today. 3 times 4 minus 5, so let's write this out. Goodness, this thing gets so tangled up so quickly. Okay, this is 3 times 2 minus a minus 2, which is 4. And this is plus 5 times 0 minus a minus 6 is 6. And this is plus 1 times 0 minus 6. This will be 12 plus 30. I didn't put my parentheses in there. Minus 6. Okay? That's a 30. That's an ugly 30. Okay? It would be 42 minus 6 is equal to 36. So every way you do it, you get those same. And let me erase mine so you can see them do it. 3 times 4 plus 5 times 6 plus 1 times minus 6. And that gives you 36. Okay. A natural consequence of theorem 1110 is that the volume of a parallelepiped is 0 if and only if the 3 plane vectors are coplanar. In other words, the 3 vectors are in the same plane. Then you don't have a volume at all, because they're all in the same plane. That is when the vectors U, which is U1, U2, V2, U, which is U1, U2, U3, V, which is V1, V2, V3, and W, which is W1, W2, and W3, only if that determinant is 0. Okay? Now, what's the consequence of that? Well, for this to be 0, these have to be perpendicular. Is that right? Yeah, the dot product would be perpendicular. And for these to be perpendicular, okay, U cross or V cross W is perpendicular to both V and W, and the only way for these to be perpendicular to each other is U to be in the same plane as V and W. So that's what they're getting at. That's all they do. And then they're through with the section. So homework assignments here are do either 3 or 5 or both. They're both at calcchat.com. Do either 7 or 9 or both. They're both at calcchat. 7's at calcview. 11 or and 13 are at calcchat. 15 and or 17 are at calcchat. 15's at calcview. 19 and or 21 are at calcchat. 23's at calcchat and calcview. 25 is a calc chat only, and then 27 is a torque problem, 29 is an optimization problem. And they're both a calc chat, excuse me. 31 and or 33 are both a calc chat, 31 is a calc view, 35 is both calc chat and calc view. 37 is a calc chat. 39 and 41 are at calc chat if you want to explore doing those. True false 43 and 45 are at calc chat. And then there's some proofs, 47 through 51. You can do those if you choose. It's up to you. And then 53 and or 55 are also proofs. All right, so now we're ready for 11.5, lines and planes in space. What was I doing there? Okay. I want to can that and go to 11.5. Goodness gracious. All right. Now, you might say, haven't we been here before? Well, close, but not quite. 11.4 was, well, everything up till now has been, vectors and the geometry of space. The whole chapter is titled that. Now we're just looking at lines and planes in space, okay? Not three-dimensional things, lines and planes. So continuing chapter 11, vectors and geometry of space. Now we're just going to be looking at lines in space and planes in space. So our objectives here is to write a set of parametric equations for a line in space. Write a linear equation to represent a plane in space. Okay. Sketch the plane given by a linear equation. Oh boy. Sketching three-dimensional objects on a two-dimensional board is always fun. And then find the distances between points, planes, and lines in space. So let's start with lines in space. I can't talk. In this figure here, 1143, consider this line up here, this line L, just going out into space somewhere, maybe right there, okay? Just heading out there in space. Okay. It happens to pass through a point right here, and this point is going to be our x1, y1, z1. A given point. We know those coordinates. And it's parallel to some other vector down here, ABC. Now they draw the ABC as coming out of the origin, so let's have it there. So this is parallel to it up here, going through that point right there. It's not on that vector, okay? So the vector V is a direction vector for the line L, and the A, B, and C are direction numbers for the line L, because that's your direction vector, okay? Now that's an interesting kind of concept here, okay? One way of describing the line L is to say it consists of all the points Q, X, Y, and Z, there's Q on that line L, for which the vector PQ is parallel to the vector V. So PQ is just some parameter T multiplied by V. So V is down here, PQ is up here. They're parallel to each other. The direction is the same. The magnitude is just a multiple of it in the same direction. So that's why you can just do the T times V. Okay. This means that PQ is a scalar multiple of V. We just said that. It has the same direction. That means they're parallel. And some multiple of the magnitude. And you can write PQ is equal to TV, which they did and what we're doing, where T is any scalar, any real number. Okay. So, the PQ, the vector PQ, is, remember, we're defining that as It's going through this point and going through some other point, x, y, z. This is a fixed point. We know those values, or we are given to us. This is your variable, q. Could be any q along that line. And those x, y, and z's are your variables. So we could write that pq as the vector x minus x1, that's the difference in p and q, okay? The x difference, y minus y1 is the y difference, z minus z1 is the z difference in those two. But if you think about that, well, that is the vector pq. The tv, not the thing you watch, but scalar t times vector v, it could be written as AT, BT, CT, where A is a component of V in the x direction, B is the component in the y direction, and C is the component in the z direction. That's what TV is, okay? Now, by equating the corresponding components, x minus x1 is equal to AT, y minus y1 is equal to BT, and z minus z1 is equal to CT, you can obtain the parametric equations for a line in space. There you have it. Variable v minus variable x minus point x1 is equal to a times t. There's a parametric equation. Y minus y1 is equal to bt, and z minus z1 is equal to ct, where t is some scalar quantity that makes that true, and your A, B, and C are your components of your direction vector V. And they also call them the directional, what do they call it? Directional components? Direction numbers. Direction numbers. Okay. So here's your theorem, 1111. Parametric equations of the line in space. A line L, any old line L, parallel to some known vector V, A, B, C, passing through the point P, which is x1, y1, z1, is represented by the set of parametric equations x minus x1 is equal to a t, y minus y1 is equal to bt, z minus z1 is equal to ct. Given, and then so solving for x is equal to x1 plus at, y is equal to y1 plus at, z is equal to z1 plus at. So, I'm sorry, ct. Good. If the direction numbers a, b, and c are all non-zero, then you can eliminate the parameter t in the parametric equations to obtain symmetric equations of the line. Okay? So what you're going to do here is, if this t, solve that for each one. So this would be x minus x1, subtract that from both sides, divided by a, is equal to, because that t is the same as this t is the same as that t, and do the same thing for this one, y minus y1 divided by b is that t, z minus z1 divided by that c is that t, and set those three t's equal to each other, x minus x1 over a plus y minus y1 over b plus z minus z1 over c. Those are our symmetric equations for a line in space. So this is the parametric equation. This is the symmetric equations. Okay? These are all equal to each other because we eliminated the t's. These have the t's in them. So here's the example. Find the parametric and symmetric equations of the line L that passes through this point, 1, negative 2, 4, and is parallel to this line, to angle vector V, which is 2, 4, negative 4. Okay? Now, they've drawn the x-axis here, the y-axis here, and the z-axis up here. Okay? Now, what you do, 2, 4, negative 4, come 2 on x, 4 on y, and that gets you this. 2 on x, 4 on y, that gets you to this point, then go down 4 here. There's a vector it's parallel to, okay? Going through that point, okay? So your parametric equations would be, just imagine any other point here, Q, on that thing. X minus 1 is equal to 2t, oh, this is your A, B, C. X minus 1 is equal to 2t. Y plus 2 is equal to 4t, and z minus 4 is equal to minus 4t. Okay. That would give you the line in space, parametric equations of the line in space that's defined by that thing there. So let's see if they got it right. X, and then they added the 1 to both sides. So I said x minus 1 is equal to 2t, so they say x equals 1 plus 2t. Y plus 2 is equal to 4t. So y is equal to minus 2 plus 4t. That's the parametric equation. And then this one would be z minus 4 is equal to minus 4t. So divide both of those sides by minus 4. Well, let's write that one down first. Z is equal to 4 minus 4t. Now, equating all these t's together, which, if we go back to the form I said originally, this already was x minus 1 divided by 2 is equal to y plus 2 divided by 4 is equal to z minus 4 divided by 4. Those are your symmetric equations. X minus 2 over 2 plus y plus 2 over 4 plus z minus 4 over a minus 4. Okay. Feeling no lunch now. I'm so lightheaded, hungry. Okay. I'm surprised that's the only, yeah, it's not the only one. Okay. There's also example 2, which, let's see if we can find enough room to write. I guess that's going to have to do us here. I need my color back. Okay, well, it's not taking it. Okay, now it did. I have to keep reminding myself. This class goes until 2:10. Okay, and the next one starts at 2:30. Okay. By the end of the term, maybe. Okay, I'll have that right. See, my morning class starts a half hour and it goes to 2:40. This one starts on the we started at 12:30, didn't we? No, my first class starts at 10 and it goes to 11:40. This one starts at the half hour and it goes till 10. And that, I get those two so crossed up, I don't know why, but I do. Just brain problems. Okay, let's do example 2. And I think we'll then do example 3. Because the next thing here is planes in space, yeah. Let's do 2 and then 3. And 4 before we start to planes in space. No. Just 2. There's planes in space is at the bottom half of that page. All right, and this one you can see Larson even though it's not on the PowerPoint, it is at larsоncalculus.com, interactive version of this type of example. Find a set of parametric equations for the line that passes through these 2 points. Wait, this is different, isn't it? Here's 2 points, negative 2, 1, 0, and 1, 3, 5. Okay. We want a set of parametric equations for the line that passes through those 2 points. Okay. Now wait a minute. Last time we were given a single point but parallel to some direction vector. Now we're just given 2 points. Okay, so what you reckon we're going to have to do here?
Go to the vector.
What's that?
Find the vector.
Okay, and what vector do you have in mind? I'll name it V. See, these are points, they're in parentheses. Vectors are in angle brackets.
So you add you subtract them.
Yes, subtract the components. 1 minus a minus 2, that'd be 1 plus 2 is 3. 3 minus a 1 is 2. And 5 minus 0 is 5. Okay. Last number 5 is sort of written against that. My word, I'm so dizzy. Okay. Oh. Man. All right. So there's a vector. What does that tell you? Okay, good idea, find a vector, but what does it tell you?
It tells you where it's going.
Okay, yeah, those are the direction numbers, okay? Those tell you which direction it's going, okay? We happen to do the second point minus the first point. If you had chosen the other way around, it would still be telling you where you're going. Just heading in the opposite direction, but still along the same line. Okay, then you pick any one of those points. Oh my goodness, be still my heart. I think I've seen this guy somewhere before. All right. Jordan's here. Good to see you. Okay. What we're doing is finding parametric equations for lines in space. Okay? And you're given 2 points, and only one line can go through any 2 points, even in space. Okay? That's true. So we got the direction of that line by taking the difference of their components, their coordinates, and making them the components of the direction vector. Okay? And those are called the direction numbers then. And then what we do is pick either one of the points, and I don't care which, okay, and use that as a sort of the reference point, and then do your parametric equation from there, okay? So, is the first point okay with you?
Yes.
Okay, so we'll do x minus a minus 2, which is x plus 2, x plus 2 is equal to, doesn't matter what parameter you choose, they tend to like t, so we'll do 3t. Okay? There's your parametric equation in x. Okay? And y, stay with the same one. Since you chose it, stay with it. Y minus 1 sorry. I was trying to, since we're using this point, y minus 1 is equal to 2t, all right, and the third equation is z, well, z minus 0 is z is equal to 5t. I think that's right now. Yeah. Goodness, my head hurts. Okay, so there are the parametric equations for this line in question. Okay? And they like to write them the other way. X is equal to minus 2 plus 3t. Y is equal to 1 minus plus 2t. And z is equal to 5t. That one's already in that form. And that's exactly what they wrote. Minus 2 plus 3t, 1 plus 2t, z is equal to 5t. Now, guess what? If you had gone the other direction and use this as your point rather than this one, then it would be x minus 1 is equal to 3t. Y minus 3 is equal to 2t and stuff. And then you've done your parametric equations. They wouldn't look the same, but if then you had gone back and done your symmetric equation, you would have seen they all come out being the same. It's just that before that, when you just imagine someone throwing those at you, say at wartime or something, and they were throwing things at you, it really wouldn't matter where they're coming from, you know, but they would basically all come out the same. That's a stupid analogy, but okay. As t varies over all real numbers, parametric equations in this determine the points x, y, z on the line. And particularly note that t is equal to 0 and t equal 1 give the original points that you had here. Certainly t equals 0 gives you x equal I'm looking at the wrong one. X equal minus 2, y is equal to 1, and z is equal to 0. If you'd chosen the point 1, then it would be minus 2 plus 3 is 1. T is equal to 1. 1 plus 2 is 3, and 5. There would be the other. So both of those points are on the line represented by those parametric equations. If you had chosen them the other way around, then the 0 would have given you that point, and either 1 or minus 1 would have given you the other point. So probably minus 1. So they would be equivalent parametric equations. All right. Let's move on from there to planes in space. Oh, this isn't airplanes, okay? This is flat planes, okay, in space. Consider the plane containing the point x1, y1, z1. That's the same point we had for a line, okay? But it has a non-zero normal vector, ABC. Now, normal means perpendicular or orthogonal or at right angles to the plane, okay? At any point in that plane, this line is going to be perpendicular to it, okay? If the plane's like this, okay, if the plane's like this, the normal line is like this. If the plane's like this, the normal line is like this. Whatever the plane is doing, the normal line is perpendicular to every line in the plane, okay? Now, that normal vector is ABC. Now, remember, we're doing lines in space. The vector that's parallel to this line is the ABC. This is a vector perpendicular to the plane, and that perpendicular vector has components A, B, C. Now this plane consists of all points Q, which in the Q out here is some arbitrary point x, y, z. Not a fixed point, x1, y1, z1, but an arbitrary point. Point x1, y1, z1, they give you that, okay? That is a specific point. This is a general point with variable components, coordinates, okay? For which the vector PQ has to be orthogonal to n. Because if P and Q are both in the plane, every line in the plane is perpendicular or orthogonal to n. So using the dot product, remember the dot product, two vectors perpendicular to each other, the dot product is always 0. So n, which is this one, dotted with PQ, which is x minus x1, y minus y1, z minus z1, that dot product is 0. And that's what they said here. ABC dotted with x minus x1, comma, y minus y1, comma, z minus z1, closed thing, that's equal to 0. Well, now what do we have? Dot product. A times x minus x1 plus b times y minus y1 plus c times z minus z1 is equal to 0. That equation of the plane is said to be in standard form. A, B, and C are your normal vector, okay? And x1, y1, z1 is any point on the plane. That's your standard form for a plane. Equation of the plane in space, okay? Just knowing the normal vector and any point on the plane. All right. So, here's theorem 1112. It states that very thing. The plane containing a point x1, y1, z1, having a normal vector a, b, c, can be represented by this standard form of an equation of the plane. A times x minus x1 plus b times y minus y1 plus c times x minus z minus z1 is equal to 0. Has to be. Now, if you regroup those terms, you obtain an equation for the plane in space. This is a general form. What they mean by this, multiply these three. AX, that's just that component A of your normal vector times the general X component, plus BY plus CZ, those are the ones that have the variables in them. A times X1 is just some number. We know this, we know that. So we know the product. We just don't know its value. So that's going to be a minus AX1 minus BY1 minus CZ1. Add all those others and make it the number D. Because those are just numbers. So that is your general form of an equation of a plane. Given the general form of an equation of a plane, it's easy to find a normal vector to the plane. A, B, C, the coordinates of your variables, okay? Simply use the coefficients, I say coordinates, coefficients of the x, y, and z and write it in that form. That's all you have to do, okay? All right. I was just going to go back. I hope this isn't confusing to you. But the coordinates, components of the parallel vector down here, where in your denominators there are the things multiplied by your parameters in parametric form. Here they're the coefficients of your variables. All right. So here's example 3, top of page 789. Find the general equation of the plane containing these points. Wait a minute. They haven't given us our normal vector, have they? Well, they don't need to, okay? Find the general equation of the plane containing these points. Now, all that's required here is these 3 points cannot be on the same line. If they were, that's not going to give you a plane, it's just going to give you a line. So find the general equation of the plane containing these 3 points. Okay? Well, what do we need? We need a normal vector, don't we? Okay. How do we get a normal vector?
Subtract.
Second?
Subtract the points.
Okay, that's how you get a vector. We can say, take these 2 points and subtract the components and get a vector that goes from that to that. You can do the same thing by either these 2 or those 2. It doesn't matter which, just pick any pair. This pair and one of the other 2 pairs, or this pair and one of the other 2 pairs. I mean, just pick any pair of points and then pick some other pair and get you 2 vectors. Okay, so which 2 you want to use? The first 2?
First 2.
Huh?
First 2.
Okay, and which way you going to subtract? Oh, here's Daniel. I think we have a majority here today for the first day in quite a while. Well, last Monday we had a majority too, I think. Okay, so what's the vector you're going to get from there? You want to give it a name?
V.
V, all right, one of my favorite vector names. Okay, V will be what? I like component notations.
1 minus 2.
Okay, 1. Once you choose that to be 1, that means it's the first minus the second. Then you have to do that with all of them. So what's the next one? Not minus 2.
4 minus 1.
Huh?
4 minus 1.
Say that one more time.
4 minus 1.
No. Once you do 2 minus 1, then you do 1 minus 4. You have to do the order the same.
Oh, I said 1 minus 2.
Oh, I thought you just said 1 was, I got it, sorry. I wasn't, well, I didn't need to do that. Okay. You did 1 minus 2, which would be a negative 1, and then you get a positive 3 and a 0. Okay. There's your vector V. That's in the plane, right? Pick any other 2 points. I don't care which 2. Let's just call them now 1, 2, and 3. You picked 1 and 2 the first time. Pick any other pair. You tell me.
So negative 2 minus 1.
Okay, you're doing 2 and 3? Okay. You want to name that vector?
U.
U. Okay. I'll name it U too. Oh, never mind. Okay. So that will be, what would be the components of it?
Negative 1.
How do you get that
Oh,
one?
no, negative 3.
Negative 3, okay.
4. 0 minus
Wait. If it's a negative 3, then that has to be a negative 4, doesn't it? If you do minus 2, minus 1, yeah, right?
Right.
Okay.
And then 4 minus 1
Is 3. Positive 3. Right, good. Okay. So there we got 2 vectors that are in this plane, right? They have the point 1, 4, 1 in common, but that's okay. No problem there. Two vectors in the plane. Okay? What else do we need?
I wasn't here last class.
Okay, no, from what we did today. We need a normal vector to the plane. Now, this part you might not know. How do we get a normal vector that's normal to both of these 2? Your cross product does that. The cross product always produces a vector, and it's vector normal to the 2. So we do a cross product of these 2. And we can do, and this again is how we do our cross product. We start with I, J, K, and repeat the first 2, I, J. Okay, it's sort of like a determinant here. Okay, and then we put these 2 down, negative 1, 3, 0, negative 1, 3. And the other one is a negative 3, negative 4, 3, negative 3, negative 4. Repeat the first 2. And then you do your down diagonals. And that's going to be a what?
9.
9i, right? Next down diagonal.
0.
0.
The 4K.
Plus 4k. Okay. Now we do our up diagonals. And what does that give you?
Negative 9K.
Yeah, except since you're going up, you negate that. So that would be a plus 9k. You see that?
Yes, sir.
Okay. Next.
The 0.
0. I like those. And then that.
Then we would have a 3J.
Plus 3j. Got it. Now you combine those together and you get 9i plus 3j plus 13k. All right. There is your perpendicular vector, which gives you your coefficients, okay, for your plane. Okay? Now, using that vector and any one of the 3 points, not the 2 vectors you had that you came up with, any one of your points. Now we can write the equation of general equation. Well, it's not going to be general to begin with. We'll start with the, what was the other one they called it? Standard equation, and then we'll get the general. Okay? So let's do the standard equation first. Remember how that went? Okay, it was 9, the coefficient here, times,
X minus X.
which one you going to use? 1, 2, or 3? Second?
1.
1, okay. X minus 2 plus 3 times what?
Y plus 1.
Right? Plus, wait. Yeah, okay. I got lost where I was. Okay. Plus 13 times Z minus 1. Okay. And that's equal to what? 0, because of that dot product of perpendicular. Okay. So that'd be 9x minus 18, right? Distribute. And what would that give you? Plus 3y minus 3 plus 13z minus 13 equals 0. Okay? Now, I don't have enough room to write at the bottom, so I'm going up to the top. That would be 9x plus 3y plus 13z. Now, they put, and it's fine with me, but I just have a little objection about it. Add the whole numbers you got. Minus 1 and minus 13 and minus 31 minus 3 is minus 34. So minus 34 is equal to 0. That's perfectly fine, but you know, why not write it this way? 9x plus 3y plus 13z is equal to 34. Same equation. Why write a minus 34 on this side and 0 on the other side? Just do that. Get all the variables on one side, the numbers on the other side. That looks like most equations we're used to seeing. Okay? Now, if one of those components were missing, you would be in a plane, because that would be a two-dimensional thing. And that would be a standard equation of a lighted plane. Not a very useful equation, but it's a standard equation. This now is our general equation, or the way I've modified it by adding 34 to both sides. General equation of a plane, because it's three-dimensional. Okay, and they're all linear. Know that x's and the y's and the z's are not squared. They're all to the first power. All right, let's see if they came up with the same one we did. They got, I can't see it now, there it is. 9x, yeah, there it is. 9x plus 3y plus 13z minus 34 equals 0. Okay, or moving it to the other side. Now, two distinct planes in 3 space either are parallel, two planes, or they're going to intersect. And where they intersect is going to be a line. Okay? So they're either parallel or intersect with a line. Okay? Now if you go, oh goodness gracious, look at this. 5 out of 7 Vince is here. Okay? We're only missing Charles and Brian. Okay. And just for your general information, I had hoped to get your letter done this morning. Friday, I carried my car to the shop. Fortunately, we had bought a vehicle up in Jasper, so that's where I take it to because they have the records and things on it. And so I took it up there, and in doing just the routine maintenance on it, they said, oh, you have a roofing nail in your right rear tire. And I had had the light come on, but all the tires looked good. You know, I didn't have a tire gauge with me, so I couldn't measure. I said, okay. And he said, that's why they just thought the gauge was off. The indicator was off. And they said, no, you want me to repair it? Oh, yeah, sure, you know. So they repaired it. This morning, got in the car to come to work. It wasn't feeling right or sounding right. I pulled over a few blocks from home. The right rear tire was flat. The tire they had repaired, I could see the plug they did in it, hadn't done a very good job. The roofing nail kept the air in it better than the plug did, you know. So, so I called the shop. Of course, they said, well, bring it by. I said, look, I'm in Birmingham with a flat tire. It's not going to be really easy for me to bring the car by. Oh, that's right. Okay. And of course, they weren't going to volunteer to come repair it either, not from Jasper, and that would have taken too long to get here anyway. And I said, well, Honda roadside, I mean, it's almost a new car. I mean, it's the second time I've had it in the shop, 20,000 miles, okay. But it's your tire. It's the tire you repaired. Well, yeah, okay. Didn't volunteer anything. I said, well, roadside assistance help. Well, that's only for mechanical parts, not for tires. But you can check with them and see. And I said, especially since it was probably your, yeah, you can check with them. So I called roadside assistance. And then they wanted me to get online with my telephone and messages, and some things it would work and sometimes it wouldn't work and stuff. And finally we did get together and finally got to talk with someone there. Or she called back, you know, once I got it. And how can we help you? I said, well, here's the thing. Okay, well, our roadside assistance only comes, I said, I understand that, but here's the story. She said, yeah, it probably was her fault, but we still can't cover it. Now, maybe you can get them to give me a call and tell me that they will cover it, and then I'll send the vehicle, you know, the truck out. Okay. How long will that be? It'll be an hour. Okay. I'd already been there 45 minutes, you know, trying to get through to everybody and stuff. So, and waiting for her to call back. I said, it sounds like to me I've got to just change the tire, which I should have done right at the beginning, but I was trying to see and document that this is your bad, not mine, you know. So finally I went on and changed the tire. For a new car, I didn't know where all the things were. And sure enough, one of the lugs, the lug wrench wouldn't work on. So I had to call the dealership again and said, what's the story with this lug? It's on every tire this way. What is the story? Oh, that's a security lug. I said, well, yeah, well, how do I get a security lug off? Oh, well, look, It could be in the glove box. It may be in the trunk. Look for a little black bag, and there's a special thing that you can get that off with. And I said, well, there's nothing in the owner's manual about that. Oh, that's a special feature. So basically, it told me a special feature that they didn't tell me about, and I probably paid for, and it was a pain in the neck or some other body part. So I finally got, found the thing, did it, and got it off, and went through all the mess. But I was an hour and a half late getting to work this morning. So things like your letter.
You got to let them go.
Yeah.
You got to get your due diligence.
Yeah, so I didn't get your letter done. That's why I'll try to work on it this afternoon if I can. I had something come up at lunch. Huh?
We got a whole other month, so we got time.
All right. All right, so anyway, this is your plane in space in what they call standard form. All right, so two distinct planes in space either going to be parallel to each other or intersect in a single line. For two planes that intersect, let's see, is this printed anywhere here? I don't want to read all this. Oh, wait. I forgot. They have a solution here. So let me clear my chicken scratch off of here, and so you can see their solution. All right, how they did to apply Theorem 1112, you need a point in the plane and a vector normal to the plane. Well, we have 3 points in the plane, but no vectors. So what do? We come up with, there are 3 choices for the point, but no normal vector. Hey, yeah, I figured that out, okay? So to obtain a normal vector, use the cross product of 2 vectors, and they used U and V, didn't they? Extending from the point, and they did the one from this one to here and to this one to there. So they used a different 2 vectors than we did. Oh, no. Will that give them a different answer? Oh, no, it won't. Okay. So they just chose this one and that. Okay, so their vectors are going to be different from ours. Theirs are going to be -1, 3, 0. Is that one that we had? I've already erased it.
Ours were -1, 3, 0.
Okay, so that one worked. This one, though, will be -4, -1, 3. That's not one we had. Okay. Oh, no. Maybe this won't work then. Or maybe we did it wrong. Let's see. So by doing that, they got -1, 3, 0. That's one that we had. -4, -1, 3. That's the other one I just said. Well, what do we do with those two? Cross product of those 2 vectors is going to give you a normal vector to both of them. And that will be normal to the plane. So it follows that a vector normal to the plane is given by U cross V. Now they did it this way. I extended and do 2 more columns. You still can do it, but here's the difference. They just, whoop, there's the answer. And look at that. Same thing that we got, isn't it? Same vector is the normal vector, no matter which 2 vectors you use. Okay, they didn't show any of the steps. Let me go back and show you the steps their way. Okay? For the I, they do 9 minus 0. For the minus j, doing it their way, this is minus j, it's the -3 minus 0. Well, minus j minus 3 would be plus 3j. And then for the k, it's 1 minus or plus 12, 11. No. Do it again. 1 minus a minus 12, that is positive 12. 1 plus 12 is 13. 13k, if I could add. Okay. So yeah, that's exactly what we got, though we used 2 other vectors, or 1 other vector. Okay, still the same. That's your A, B, and C. So then you take that, plug it in, pick any point, and they use the 2, 1, 1, which I think is the one you chose too, wasn't it? So they do A, so the rest of it's going to be the same. A times x minus x1, which is going to be our 2, plus b, which is our 3, y minus y1, which is 1, and plus 13 times z minus z1, which is 1 again. So 9 times x minus 2, plus 3 times x minus 1, plus 13 times z minus 1. Same thing we did. That gave them 9x minus 18, plus 3y minus 3, plus 13z minus 13. And when you add all those together, you get 9x plus 3y plus 13z. Those are the variable terms. Add the constant terms together, you get minus 34. Okay? Okay, and here it is. Okay, this is what I was just starting to read and said, surely they've got this on the slide. 2 distinct parallels in plane, either parallel or intersect in a given line. Okay, for 2 planes that intersect, you can determine the angle of that intersection, and this is the acute angle between 0 and pi halves, acute angle, not the obtuse angle, but the acute angle between them from the angle between their normal vectors. Because if one of them has a normal vector like this, the other one like that acute angle in between. Not the obtuse angle this way, but the acute angle that way, you can get. And how do you think we get that? Well, it's either going to be a dot product or a cross product. I think the dot product's easier, and sure enough, that's what we have. Specifically, if the vectors n and n1 and n2 are normal to the 2 intersecting planes, then the angle theta between those normal vectors is equal to the angle between the 2 planes. And that is, and just to get a reminder of this, the dot product of 2 vectors is the magnitude of one times the magnitude of the other times the cosine of the angle in between. So that's where that comes from. We keep everything positive. The denominator is always positive. Both magnitudes are positive. Sorry, I've got hiccups. The dot product could be positive or negative. Just take the absolute value. And then you've got the cosine. It's going to be a positive number. That's going to be an acute angle. The antiderivative of the inverse cosine is going to be acute. Consequently, 2 planes with normal vectors n1 and n2 are perpendicular when those are the dot product is 0, because then your cosine of 90 would be 0, so pi halves. Parallel when n1 is a scalar multiple of n2, because then they're the angle theta would be 0. All right. I'm sorry, I said that backwards, didn't I? Parallel when the angle is when they're scalar multiples. Then, yeah, because then the cosine of theta is equal to 1, and the cosine of 0 is 1. That's what I was trying to say. I said the wrong thing. I think they skipped any examples here, didn't they? Yeah, they skipped example 4. So let's go back and see if we can do example 4. Okay. How are we doing on time? Got a little over 10 minutes, right? All right. Find the angle between the 2 planes, x minus 2y plus z is equal to 0, and 2x plus 3y minus 2z is equal to 0. Now, one thing to notice about these 2 planes. Anything you pick up on? Can you give me a point that those two planes go through? Anybody? X equals 0, Y is equals 0, C is equals 0. Right? Yep. That fits for this one. That fits for that. How I picked up on that was to notice there's no constant here and no constant there. If there was a constant, then these planes don't go through the origin. Both of these happen to go through the origin. But they're not multiples of each other, so they're not parallel. They do have an angle in between. Okay. Now, what would we need to do to determine the angle between them? We need to know their normal vectors, right? But what are the normal vectors? What's the normal vector for the first one? Can you read it to me? Let's go back somewhere here. Here we go. Here we go. If you have this form, now we have to have d is equal to 0. That's what we have. This form right there is equal to 0, right? On both of those things. The normal vector is A, B, C. The coefficients of your variable. Right there. The general form is easy to find. The normal vector in the plane, simply use the coefficients of x, y, and z and write it down. So that's what we get to do here. It's that easy. I wish I could find some way to make it harder, but I just can't. Your normal vector for plane 1, let's just call it that, is what? You tell me. 1, negative 2, 1. What's the normal vector for the second one? 2, 3, negative 2. You got them. Okay? So what do we do to find the angle in between? All right, right, yeah, okay, you got it. Say again?
Do our IJK, IJ.
No, that's cross product. We're dealing here with dot product. The easier one. Don't have to do IJK, just do them. It's the dot product of the two normal vectors divided by the product of their magnitudes. Right? So we got three things to do. What are they? Find the dot product and find the two magnitudes. So let's go back. All right. Which you want to do first?
Dot product.
Dot product. So N1 dot N2. Oh, and by the way, I should have vector symbols over them because I can't write bold. Okay? That's a 1 there, not another dot. What's a dot? Oh, it's not a vector. A dot product gives you a scalar number answer. And what will it be?
2, negative 6.
2 minus 6 minus 2, which is negative 6. But we want the absolute value of this, so that would be 6. So there's your numerator. Now all we got to do is get the denominators. Well, denominator, one part of it is magnitude of N1, which would be square root of
1 squared.
Yeah.
Plus negative 2 squared. Plus 1 squared.
Okay. Square root of 6. Magnitude of N2. I keep forgetting my vector symbol. The square root of 4 plus 9 plus 4. And that would be square root of what?
Oh, wait, no.
17. Okay. So, I think we got it now. The cosine of the angle in between is equal to, writing another set of equal signs. I don't know why I've done that twice or 3 times a day. Okay. It's going to be 6, that's the dot product, divided by the product of these two, which is the square root of, goodness gracious, is that 42? No. 102? Is that right? 6 times 17? I think that's right.
Yeah, 102.
Okay. So, while you got your calculators out, do it. 6 divided by the square root of 102. That's going to give you some decimal number, hopefully between -1 and 1. In fact, I know between 0 and 1. And then take the arc cosine of it. But be sure you're in radian mode. Well, I don't know. What mode are they in? Nope, they go in degree mode. So get in degree mode. Slow calculators, aren't they?
I'm trying to do it on my phone.
Yeah. You're calling in the answer?
0.58.
Okay. Okay, you got that as the theta or cosine theta?
That was cosine.
Cosine theta, they have in the book 0.59409.
I sort of rounded because I was having to do it backwards.
What's that?
I sort of rounded because I was having to do it backwards.
Oh, I see. Okay. Okay. So yeah, and then when you take the arc cosine of that, what do you get?
Can't do that one.
Okay. What you get? Anyone? Huh? Inverse cosine. Be in degree mode. Anyone got it yet?
53.9706.
They got 53.55. I don't know. That's close enough. Because frankly, they don't have but one significant digit anywhere, so I don't know how to get 4 out of it. But anyway, about 53, 54 degrees. Okay, something like that. Okay. Let's see what they say here. You can find the line of intersection of the two planes by simultaneously solving the two linear equations representing the planes. One way to do that is to multiply the first, okay. They didn't ask you to do this, but they're doing it. Oh, no, they did. I just stopped at the first and found the angle between. Then find the parametric equations of their line of intersection. Okay? Well, parametric equation for the line of intersection. Can I erase most of what I got here because I've written all over the page and it's going to be hard to see. So let's get rid of this. I hope I won't need it again. If I do, I'll get you to tell me what the things are so I don't have to redo them. Okay, are we out of time? Oh, we almost are, aren't we? I'll try to make this as quickly as I can. You got to go to work? Okay. All right. So what we would need here, it says to find the parametric equations of the line of intersection. What you would need, one thing is they say it's sort of like solving a system of equations. Multiply this by -2 and add to that one. Okay, so this would be a -2x plus 4y minus z, no, minus 2z. Whoa, look at that, is equal to 0. Okay? And when you add them, you eliminate the x. So you have 7y minus 4z is equal to 0. Okay? Now, which way you go? They go with the solve for y. Y is equal to 4/7 z. Okay. Now, plug that into either one of the original equations, and you have, which one's better? Maybe this one. X minus 2 times 4/7 z plus z is equal to 0. So that gives you x minus 8/7 z plus z is equal to 0. So this gives you x minus 1/7, because 1z is 7/7 z, minus 8/7 plus 7/7 is minus 8/7 z is equal to 0. So x is equal to 1/7 z. Okay, well here's your ordered triplet then. 1/7 z, 4/7 z, and z. But to get rid of the denominator, let's multiply everything by 7. Z, 4z, 7z. So there's your parametric equation. Well, not quite, but close to it. Just let z equal some variable t, and that would be t, 4t, 7t, rather than z's. And then what? That's a 7, not a zz. Okay. And then you have x equal t, y is equal to 4t, z is equal to 7t. Now, it seems like you need to have... Yep, that's all they do. Okay. All right. And we'll stop there and pick up with sketching planes in space next time. I'll put the assignments on this so you can hear it if you want to. All right, homework exercises here will be number 5. It should be at calcchat.com. Any of the odds 7 through 11, they should all be at CalcChat. 9's at CalcView. Either 13 or 15, they're both at CalcChat. 15's at CalcView. Any of the odds 17 to 23, they're all at CalcChat. 25 or 27, they're both at CalcChat. 29 or 31, they're both at CalcChat. 33 or 35, they're both at CalcChat. 37 should be at CalcChat. Any of the odds 39 to 43, they should be at CalcChat. 39's at CalcView. Any of the odds 45 to 55, they should all be at CalcChat. 47's at CalcView. You might stop there. We'll pick up the rest of those next time. Good deal. Okay. Oh, I was wondering why there weren't any constants in there. Remember, both these planes go through the origin. That means the line of intersection goes through the origin. There's why there's no constants for it. I forgot that. Yeah. All right. Take care. I want to.
Question. What are all the changes we're going to be doing
Now, what's this one more time? Say again?
What are all the chapters we're going to be doing in this class again?
In this class?
Yeah.
Well, we're going to have a test really soon on chapter 11 when we finish this section. I'm going to try to have it ready for you next time because 11.6 begins, it's strange, but that's in the next, is combined with chapter, is it 12? Yeah, 12 is vector value functions. So 11.6 goes with 12. Strange but true.
So 8, 11, 12.
Wait. That's right. We did do some in 8 that we haven't been tested over. Is that what you're saying?
Oh yeah, you already.
Yeah. Yeah, we did a little bit of 10, but nothing that we're going to test you on, right? What were you saying? What have we covered so far? Let's see.
Yeah.
Yeah, we didn't do infinite series, or did we do any of those? I don't think so. Let me just look at the table of contents. Okay. I tested you on chapter 8 already, didn't I?
Yeah.
Oh, okay, right. In chapter 9, we did 9, 1, and 2. And 10, we did 2, 3, and 4. No, we only did 2 and 3. We did a little in 1, but I'm not going to test you on that. I just wanted to expose you to it. We did 2 and 3. Okay. And then in 11, it's 11, 1 through 5. Because 11.6 we're going to do with chapter 12.
So we're not going to be testing stuff at 9 or 10, just...
No. 9, 1, and 2, 10, 2, and 3. Those 4 sections there, and then the first 5 and 11.
Okay.
Yeah. I'll try to have that ready for you next time. Knock on wood. Okay.
Thank you.
All righty.
Have a good one.
You too.